Thank you very much. I want to just to start by wishing Pavel happy birthday in days like that. My memories goes to the first time I met Pavel, which was something like between 35 to 40 years ago. He was a young student of Melnikov at that time. I came for a visit to Minsk. And I even remember he invited me to lunch in his home. And at that time, he has one little baby. I'm sure this baby by now is, is a big guy. And ever since then, we were in a close contact. I must say that I was almost shocked to get the invitation to his 60th birthday, because somehow it's like in relativity theory for me, because he's younger than me, much younger than me. He's always much younger than me. So it's quite shocking to see that the young boy is already 60. But my talk might suit you, Pavel, because I want to convince you and some of the others that there are kind of new directions of research for people who love pro-finite groups and residually finite groups, like the two of us and the rest of the audience. So my title on the face of it has nothing to do, but I think that during the talk you will see that it's that there is a pro-finite and residually finite thinking in this subject, and all this connection between the finite and the infinite in group theory. So so I want to kind of to do some public relation to this area, which I got excited about this a few years ago. In the last couple of years, I spent quite a lot of time of it. So let me start right away with the result that got me to start to think about this subject. This was a paper of Golnara Argesteva and Ponesco that I came across in some sense accidentally a few years ago, like 5-6 years ago, which says the following. Let's say it carefully. The statement is very simple, actually, to state. For every epsilon, there exists delta, such that if A and B in the symmetric group are two permutations in the symmetric group on n elements, and you should think about n very large, like n going to infinity, satisfying that the distance of the commutator, the identity, is less than delta. Namely, the commutator is very, very small. It's not the identity maybe, but it's very close to the identity. Then there exist A prime and B prime, there exist permutations such which are very close. We can correct A to A prime and correct B to B prime. The distance between them will be less than epsilon, between A to A prime and between B and B prime. And A and the commutator of A prime and B prime is exactly the identity. Namely, A prime and B prime truly commute. Namely, to say this statement in short, every two permutations which are nearly commute are near commuting elements, are near commuting permutation. The matrix we are using here is the normalized Hamming matrix, which is the distance between two permutations is 1 over n, the number of I in n, such that sigma of I is not equal to tau of I. So that's the natural matrix in how many places they are different than each other. Okay, where this theorem came from? Actually, their they were kind of inspired by a long tradition in mathematical physics. In mathematical physics, there are many papers of the following, which interested in the following. If you have A and B are two n by n complex matrices, and sometimes they want to take complex matrices satisfying some properties, say self-adjoint or unitary, or just any matrices, assume they almost commute. Now, in the matrices, to say almost commute, it can be with respect to many different norms. You can take the Hilbert-Schmidt norm, you can take operator norm, etc., etc. The question is, are they near with respect to this norm matrices? Sometimes you want them not just to be near matrices, but near matrices with the same property, which truly commutes. For example, so there are dozens of papers of this kind. You have, let's say, you have two unitary matrices which almost commute with respect to the Hilbert-Schmidt matrix. Then they nearby, in the Hilbert-Schmidt matrix, nearby matrices, unitary matrices which truly commute. By the way, this is true. This is a theorem. It's a non-trivial theorem. On the other hand, it's not true for the operator norm. There are examples. It's also not so trivial. There are examples of matrices which are nearby, which almost commute in the operator norm, but they are not nearby commuting matrices in the operator norm. Anyway, they got interested in that and proved similar results of that kind for permutations. But now you can immediately think about the generalizations, like we are always very good at, mathematicians, know to generalize. And you can ask the following question. Assume you have x be x1 up to xd. Think of it as a set of variables, and R will be words in the free group on D generators. We have here D generators. We take words in the free group. And we can think of it as a system of equations. Namely, we ask ourselves the following. Assume, okay, let me get the definition. This system of equation, we say that it is stable system if for every epsilon greater than 0, there exists delta greater than 0, such that if you have permutations A1 up to AD, all of them in the symmetric group on n elements, such that all the equations are almost correct. Namely, dn, the distance, the normalized Hamming distance of Ri A to the identity is less than delta. Then there exists true equations. Then there exist true solutions. There exists A1 prime up to AD prime in the same symmetric group N, which are very close, epsilon close to the original one, which truly satisfy the equation. Okay? So that the previous theorem which I gave you was a theorem that if the equation is just the commutator, then the system of equation is stable. In fact, there was an observation even before that who studied this type of problems, and the Glebsky and Riviera, in a little paper which was unknown, at least to me, till then, already in 2009, which appeared in the Taiwanese Journal of Mathematics, they prove that the stability of R, you see, R is this set of equations, and we want to ask whether this set of equations is stable or not. Equations in permutations. The stability depends only on the group gamma. which is presented by X and R. Just take the group gamma presented by X, these generators, and the relations R, then the stability depends on the group and not on the system. Namely, assume the same group as a different presentation by generators Y and relations S, and you think of S as the system of relations, even if it's not different number of generators, different number of relations, if one system is stable, then the other one is stable. Which means that the stability depends on gamma, namely this is a group theoretical business, right? This is a group theoretical property, so we are now in group theory, the kind of group theory that we like, and we really want to understand which groups are stable and which groups are not stable. Right, so now I can ask it on any group. Take your favorite group, and then ask which one, is it a stable group? If your favorite group is a surface group, then ask, is a surface group stable? Namely, is this one relation defining it is stable? If your favorite group is SL3Z, look at the presentation of SL3Z and look at the equation. And then, usually direct methods are very difficult and are almost impossible. Now, because I have only 50 minutes and not 60 minutes, then let me just say it without going on to the details. It's not difficult. So the way I presented the notion of stability, it defined for a finitely presented group, because R and S are finite, but it's not difficult to generalize to the notion to any finitely generated group and to ask whether it is stable or not, a definition which for finitely presented group will be equivalent to the previous one. If you can get it quickly, fine. If not, I will send Sheila. I bet you will have a website of the. Well, I am sure it's recorded, so you can see this. If you're really interested, you can see this slowly after that. So the basic question now is, and that's when a group gamma is stable and when it is not stable. So the work of Lubotzky and Riviera and Ardasheva and Ponesco made several basic results. Well, of course, free groups are stable. This is trivial. Like there are no relations, right? So the relations are if there's no relation, then every almost solution is nearby a solution. Lubotzky and Riviera prove that finite groups are stable. It's not difficult. But nowadays it's maybe easy result, but at that time this was the first results in this direction. And the theorem I brought you before about two permutation was actually more general, and basically it said that abelian groups are stable. So in the last few years there was kind of a revolution in this area, but I really want and we know much more. I want to stress that these two papers were very influential, at least on me, and maybe on also on others. And in a few minutes, I will show you how much grew up out of that. But at that time, and that paper, it was just like 5 or 7 years ago. So little was known that it was not even known if you take an abelian group cross a finite group, and everything is finitely generated, right? Like, is this stable group or not? Now there is a very important motivation. I mean, I think that the question by itself is very natural and nice. But the dramatic motivation to study this, that all this line of research is can help maybe the path to prove the long-standing problem whether every group is Sophic. I'll remind you in a minute what is Sophic. I will give you a proof of the following observation. That's probably will be the only proof I will give during the talk, maybe another little one at the end if I have time. If gamma is a Sophic group, I will explain in a minute what is a Sophic group, which is stable, then gamma must be residually finite. So now we are getting, you see, we are getting to our dear residually finite groups, which means that if you will find one example of a stable group which is not residually finite, then you will solve this long-standing open problem whether every group is Sophic. Let's recall the definition. So we all know what is residually finite. Let me repeat it in a slightly different language because I want to define Sophic in a slightly different language. So what is a residually finite group? Gamma is residually finite group. I want to write it like that. If there exists a sequence of homomorphisms from gamma to the symmetric group, homomorphism, such that for every non-identity element, the distance between psi n of G and the identity is equal 1 for all n sufficiently large. If you think about it, this is equivalent to the definition of residually finite, because we know that residually finite means that you can separate the group by finite quotient. Every finite quotient can be embedded by Cayley theorem into the symmetric group on itself. And then every non-identity element has no fixed point. So the distance between it and the identity is 1. So this is residually finite. A group is Sophic if there exists gamma, if there exists phi n from gamma to the symmetric groups, map which are almost homomorphisms in the sense of what I said before, delta and epsilon. If you will see what I said before, it exactly means the following, that for every G, H in gamma, a phi n of GH is not necessarily equal to phi n of G times phi n of H, but the limb when n goes to infinity, the distance between phi n of, here by mistake it's written Y, it should be G, phi n of GH and phi n of G, phi n of H, the limit is 0 and it should be separating by almost homomorphism. So a group is residually finite if you can separate it by homomorphism to the symmetric group, and a group is Sophic if you can separate it by almost homomorphisms to the symmetric group. It's well, of course, it's clear that every residually finite group is Sophic. It's also amenable groups are Sophic, etc., etc. But there are many groups which are known to be Sophic, and there is no single group which is known to be non-Sophic. That's a major open problem going back to Gromov, which became more important over the years, even much more than it was originally. I don't have time to discuss this. Now let me prove the observation, the Glebsky-Riviera observation. If gamma is a Sophic group which is stable, then it must be residually finite. Why? Sophic means that there exist almost homomorphisms which separate the group, right? Stable means that every such Sophic group, every such almost homomorphism is nearby a true homomorphism. So just change it a bit, and then these two limits still continue to hold. So you change it a bit, and you got to the first definition. You got that it is residually finite. if you see it for the first time, might be a little bit too fast, but it's really a trivial observation, but it's very, very influential observation, which suggests taking this as a method to prove non-Sophic. Just to say, there have been other questions about groups which are approximated by almost homomorphism to unitary groups, etc. Some of their problems, this problem were recently proved by this technique, by this observation. I mean, it's each piece of work like that is very difficult and pretty deep, but at least I think here there is a chance. So as I said before, the corollary is that if gamma is stable and not residual or finite, then it is not Sophic. And this gives a potential method to ask this problem of Gromov and Benji Weiss from the 80s. And as I said, in the last few years, this philosophy was implemented in other categories, but still open for these Sophic and symmetric groups. And I will not elaborate now. Let me say very, 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 very quickly something about I mean, to be honest, I don't know how if the audience will be very interested in that, but I have to admit that when I saw the original paper of Gulnera and Pilview-Ponesco, what was clear to me, the connection to a property testing in computer science, something which I was independently interested, and I saw. And I told myself, oh my God, we can develop here a theory which combine two of my loves, you know, this group theory and this property testing in computer science, which could be a topic for a completely different talk. Let me just say something very, very quickly. What is property testing in computer science? This is maybe the deepest, I'm not exaggerating, area in theoretical computer science, which even have some down-to-earth application. Let me define what is Q epsilon testability. Let A be a finite set. Let Pn be some subset of A to the n. So the way you have to think about it, that A is a fixed set, and you look at A to the n, large power of A when n go to infinity. Now you want to check the following property: the membership of alpha in Pn. I give you a vector alpha in A to the n. Frankly, the most interesting problem, the one which I worked on for a couple of years, and eventually with few other people we managed to solve it, is the so-called to construct locally testable code. And so A is just 0, 1 to the n. It's the vector space of dimension n over F2, and we have a code. The code is basically a subset, just a subspace A, and the membership of alpha is testable. Namely, you say that the membership is testable, or more precisely is Q epsilon testable, if there exists some positive epsilon fixed and fixed Q, and some random algorithm which we call tester, which queries only Q independent of n coordinate of alpha. Answer is yes if alpha and n, and answer no with probability proportional to the distance. Let me say it in a simple word. You have a vector in a very large vector space, and you want to ask, is this vector in a subspace or not? But I allow you to read only 70 bits of that vector. Can you decide this? The feeling is that this is crazy. This is, of course, important, right? This is, of course, impossible. So actually, that's not quite true. It's impossible because it's impossible, but if you allow a little, if you allow me a little error, then it's possible. I don't want to elaborate on that, but this is related to, maybe you heard the what's called PCP, provable checking proofs, and all this. So this. Now, I think about this problem as a property testing. Why? Let's go even to the original problem. What does theorem say? The first theorem that we saw today. He said, I claim that this theorem in the computer science language says that given two permutations, I can decide if they commute by reading only 70 values of the permutation, and can be million. I will pick up 70 random i's, random x's between 1 and million. I will check if AB of x equal BA of x, and if I win, if all of them commute, then the two permutations should be nearby commuting matrices, because I'm checking, and because the theorem tells me that if they almost commute, they are nearby commuting matrices. And there is something highly non-trivial in this story, and that's kind of a property testing results. Okay, but let me continue because our time is running. So the basic problem from now on we want to study is okay. Let me maybe another observation. Then of course, okay, it's not a stability implies the stability. For some time we thought that they are equivalent. That's not true anymore. They are not equivalent, but testability of equations, I can formulate testability of equation, is also a property which depends only on the group and not on the system of equations. So from now on, I can talk about testable group, and I can talk about stable groups, and basically. Okay, so as I said, the stability depends not on the relations, but only on the group, and the program and the main goal and the rest of my talk will be devoted to partial solutions to this question, is develop methods to decide for a given group, it is testable, it is stable, etc. So I want to summarize, so it's going to be basically a survey talk from now on what are the known results. Let's assume first that the group gamma is amenable. Every amenable group is Sophic. So from this, if we will find amenable group which are not stable, that's not going to help us to get a non-Sophic group, but still it's an interesting by itself. Let me recall what is what is an amenable group. Amenable group is, say, let's say finitely generated all the time. You can extend it, but it doesn't matter. I let gamma be a finitely generated group generated by a finite set S. Then it's called amenable if for every epsilon greater than 0, there exists a finite set in gamma such that if you multiply S by each of the generators, then the symmetric difference between S and F is very small. Is epsilon part is less than epsilon, the size of it is less than epsilon, the size of F. So just think about it. Z is amenable because you can fix epsilon. You can take a huge interval between minus n and n. The generator is 1, and if you move it just by 1, then you hardly move the interval from itself. And the same thing for z to the n, the same thing for every solvable group is amenable, etc., etc. Together with Oren Becker and Musayev, these are the two people with whom I study the connection with properties testing. We prove that indeed testable. That's not so difficult. It needs a proof, but it's not so difficult. It's slightly more difficult maybe than stability, but we prove that every where I am now. I lost my yeah. We prove that every amenable group is testable. Okay, so well, when I said that the group is not so difficult, this is actually a little bit lying. It's not so difficult for us because we use some very deep results of Orenstein and Weiss and Newman and Salter about hyperfinity of amenable group, etc. So if you so it's really a difficult proof in some sense that every amenable group is testable is a difficult proof. The story with stability is more interesting because it's not, because some amenable groups are stable and some amenable groups are not stable. Let me first state the theorem. This is a joint work with Oren Becker, the same Becker here, and with Andrea Tom. And this was actually done even before this one. And we prove the following, that a finitely generated amenable group, if and only if the finite index, you feel, IRSs, I'll explain what does it mean, of gamma are dense in the space of all IRSs of gamma. Let me recall and say what is an IRS. An IRS, invariant random subgroup on a group gamma, is a subgroup that was defined only, I believe, 15 years ago or something by Abert, Glasner, and Virac, and found out, and it found out a lot of completely unexpected applications, and this is one of them. They wanted to generalize the notion of a normal subgroup of a group, and they came up for some good reasons, which I will not explain now. And we came up with this notion, IRS, invariant random subgroup, mu on a group gamma is a probability measure on the compact space of subgroups of gamma, which is invariant under conjugation. The subgroups gamma, right? We can look at all subsets of gamma. All subsets of gamma can be identified with 0, 1 to the gamma, right? I mean, like 0, 1 to the gamma. Every subset identified with such a vector, giving 1 if you are in the subset and 0 not. In particular, the subgroups can be considered as a subset of that. And if you think about it, by Tikhonov theorem, this is compact, and the subgroup, sorry, is a closed subset, so they are also compact. So we have there is a nice compact space of all subgroups of gamma, and if mu is called is any probability measure, namely a measure on the space which total measure 1, which is invariant under conjugation. If the measure is the delta measure at one point, this is exactly a normal subgroup. A normal subgroup is an invariant random subgroup such that the support of the measure is on one point. One can define, so every n in gamma define a Dirac measure which is just one. Mu is a finite index invariant random subgroup if the support, if it gives positive measure only to finite index subgroups. To get many more invariant random subgroups, you do the following. Assume gamma is acting on some probability space in a probability measure preserving way on a probability space. You can take the stabilizer of random point, and this give you IRS, and they prove that every IRS is obtained like that. That's not so important for us. I just show you how you get non-trivial example, like 1 and 2 are the trivial example. These are the other example. And the criterion for stability, strangely, is that the finite index IRSs are dense in the space of all IRSs. There is a natural topology on the IRSs, and we say that the finite index are dense. This equivalent to being amenable. Now, I want you to get the feeling that there is something here which is little bit like residually finite, right? That in some sense, we are saying that the finite index subgroups kind of teaches or control the globally the group. Okay, so this is the theorem we proved, that the two properties are equivalent, and then we were able to use it to expand very dramatically the knowledge about stable group. You remember I mentioned to you that before that it was not even known if abelian by finite group cross finite groups are stable, let alone abelian by finite. Now we know that polycyclic by finite and the Baumschlag Solitar group are stable, etc., etc. I don't want to go. I just want to call attention to the following, that not all amenable groups are stable, not even all solvable groups are stable. Here is an example of a group, of a solvable group which is not stable. This is a lovely group. The group described here was defined by Herbert Abels in 1979 for completely different reason. The advantage of being old, that you remember some old papers from the time you were a student. I was a student at that time, and I was interested for a completely different reason in that group. It turns out that that group is not stable, and the kind of the real reason, and you see why the whole subject, even though I don't have time to explain in details, is related to profinite groups. The real reason that this is not stable is because this group has a finitely generated normal subgroup, in fact, even central subgroup, which is not closed in the profinite topology. And here is a proposition, just you see that the subject is intimately related to profinite groups. If a group is stable, then every normal finitely generated normal subgroup, finitely generated as a group, not as a normal subgroup, every finitely generated normal subgroup must be closed in the profinite topology. So if you find an example which is not, then you are not stable. Now, if you look at this for a second in this group, you can see easily that this group is solvable of solvability length 3. Let me pose two very interesting problems. One is characterize the solvable stable groups. That's very natural. But I dare to make the conjecture that this group, in a way, is a minimal non-stable among solvable group. I want to claim that, to conjecture, not to claim, that meta-abelian group are stable. I love this conjecture, and I'll tell you why I love this conjecture. Remember, a stable group which is not residually finite, you remember, will be non-Sophie. But amenable groups are Sophie. So an amenable group which is stable must be residually finite. Namely, a solvable group which is stable must be residually finite. So if we the conjecture that meta-abelian groups are stable is a far-reaching extension, strengthening the classical theorem of Philip Hall that meta-abelian groups are residually finite. What I think would be, if somebody would prove it, especially if we will use these IRSs for that, then it will be a great proof. Why? If you remember, Philip Hall proved that meta-abelian groups are residually finite was not really group theoretical. The way he looked at it, he looked at the derived subgroup as a module for the commutator subgroup, and he proved that because the group ring of a commutator abelian group is Noetherian, there are theorems about modules about Noetherian groups. Then it deduces the residually finite. So it was kind of proof using a commutative algebra. Now it would be great if this more stronger statement would be proved by this dynamic and ergodic theory. I would love it if somebody can do it. Meanwhile, we indeed use ergodic method and dynamic of Lindenstrauss. This is the Lindenstrauss, the son, Elon Lindenstrauss, the Fields medalist. Some results in his thesis, which was done under the supervision of Benji Weiss, was crucial for our proof. We were able to prove that the Lamplighter groups of all kinds are stable, and also many other groups, but we could not even prove that the free meta-abelian groups are stable. But a young guy, a young Japanese graduate student, just put a paper on the archive a few weeks ago. I hope I will pronounce his name correctly, Ishikura. He proved that free meta-abelian groups are indeed stable, but still fell short from proving the conjecture. Okay, another direction. That paper of proving theorem 4, my joint paper with Aryeh Levit, that we proved that the Lamplighter groups are stable. Lamplighter groups are not finitely presented, and these were the first group which are not finitely presented, which were put to be stable, but but also Zheng was the first. More or less at the same time, we put the two papers on the archive, and she showed that the Gregorchuk groups are stable. The amenable, the classical Gregorchuk group are amenable. And in fact, she was interested she was interested in classifying the IRSs of the Gregorchuk groups. And then she heard about our work that this gives stability, and very quickly she could show that the Gregorchuk groups are also stable, which was a very nice result. And in fact, she could prove something which we also proved in a different paper, that there exist uncountably many stable groups. So this is in 2021. I want to say that it's kind of amazing that 5 years before, the only stable groups which were known were free groups, finite groups, and abelian groups, and suddenly now we have uncountably many. Cheng, the results, this theorem was proved completely different. Cheng proved about you know, Gregorchuk-like groups. Nowadays they call no. What's the common language of these groups on acting on roots? You know, like an old guy. Fractal, you know, that many of these fractal groups are stable. And we prove, actually, it's kind of cute to mention, because we went to the big masters. Again, good to be old to remember. B.H. Neumann in 1937 wanted to prove the following results. He wanted to prove something which nowadays is maybe easy, that there exist uncountably many two-generated groups. It's not completely trivial. And he constructed them. He took a product of the symmetric group, and he takes subset of it take an infinite subset. It take the total product over n in M of the symmetric group Sn, and inside that it took two elements. One is tau equal tau n, with tau n is 1, 2 in every coordinate, and the other one is sigma equals sigma n, with sigma n is the full cycle, 1 up to n in each coordinate. And he showed that all of them are different. Like for different M, you will get a non-isomorphic groups. So there are uncountably many infinite subsets. So you get uncountably many two-generated group. In a joint paper with Benji Weiss in 1993 for completely different reason, related to expanders, etc., that I will not mention here, we proved that these groups are amenable. And now, in my paper with Levitt, it's not completely trivial, but we studied the IRSs on these amenable groups and proved that they are all stable. The Jenk example are branch groups, not fractal. I think some people maybe still call them fractals, but I think nowadays branch group is the common name for them. Okay. I hardly had any time left. I'll go to the other extreme for a minute and assume that gamma is Kazhdan property T. What means Kazhdan property T? Kazhdan property T is a very important property of gamma, which is kind of the other extreme to amenability. A group is amenable n property T if and only if it is finite, so kind of a trivial, but usually they are very different than each other. And so Kazhdan property means that every non-trivial, irreducible, unitary representation of gamma is bounded away from the trivial representation. If you know what is it, fine. If you don't know, just remember that it implies that every two finitely generated, irreducible, unitary representation are kind of bounded away, are far away from each other. And for example, SL and Z as property T if n greater or equal 3, but n equal 2 does not have property T. And with the same Oren-Becker, we prove that if a group gamma is sophic, for example, if it's residually finite, if it's linear, for example, SL and Z, with property T, then they are not stable. With Mosayev, we proved that they are not even testable. And you don't have, you don't need the T, it's enough tau if you are familiar with this. I wanted to bring the proof, but I don't have time to. I wanted to bring the proof in order to embarrass me. Why in order to embarrass me? Because the proof shows that we are kind of cheating. The proof shows that we are proving that it's not stable in the following sense. You remember stable means if you have almost solution in the symmetric group N, you have to repair it, to correct it with the same N. The way we prove it, we are cheating. We take true solution in n plus 1, we kind of delete one, and we think of it as permutation on Sn. Of course, they are not solutions anymore, but they are almost solution, and we show that we cannot repair them. But the fact that we were cheating, well, formally we answered an open problem, but we felt that it's kind of not right. And it caused us to define the following notion. I want to still, I know that my time is over now. I will still another 2 minutes just to give the definition, basically, of something which what we call now flexible stable, which might be even more important than stable. Flexible stable means that if you have an almost action, like an almost homomorphism, then you can correct it to a true homomorphism, but maybe paying a little price. Maybe you cannot do it in sim n, you can do it with sim capital N when n is slightly larger than the original n. So we prove that SLN they are not stable, but maybe they are flexible stable. To be honest, so far we don't know any example which is a flexible stable and not stable, but Levitt and Lazarovich and Minsky prove, for example, the surface groups are flexible stable. And let me just finish with the following results of Bowen and Barton, which I really love, because they say it's kind of surprising and crazy. It's a conditional theorem, but they say the following: if you would prove that SLNZ is flexible stable, you remember, I told you they are not stable, but if they're flexible stable, then there exists a non-Sophie group. Not SLNZ will be the non-Sophie group. SLNZ is, of course, Sophic. It is residually finite. But somehow they showed if it's not flexible stable, they constructed some amalgamation of SLNZ with itself over some subgroup and proved that if it's flexible stable, then that group is not flexible stable and even not Sophie. Okay. I will finish here. Thank you very much for your attention. And Pavel, I over the years I learned from you quite a lot. Sometimes you follow my footsteps. Sometimes I followed your footsteps. And I'm giving you as a birthday present, because in the next 6th year, if you want to do a little switch but stay in within pro-finite alike subjects, so I think stability is a great subject for that. Thank you all. Thank you all.
Some questions, comments?
Hi, Alex. So my question, you mentioned surface group, but what do you know about other one-related groups? The flexible stable or other?
But one-related groups?
Yes,
Yeah, I mean, it's extremely interesting because on the face of it is the most elementary question. You can go back, you look at the relation and ask and work with it directly. Maybe I don't need all this fancy group theory. I can take relations. We don't know. There is one paper of Tatiana, what's her name? Schulman, and a co-author, I forgot his name. They study the stability of, I told you all this, I could give you a different talk, completely different, which would be parallel to that talk, studying stability with respect to unitary groups and let's say symmetric on the unitary group. And they managed to prove some results in that category for one-related groups, but we know almost nothing for one-related groups except of these results of Lazarovich and Leviton-Minsky, which is a beautiful, beautiful, beautiful paper. But the way they prove it is using the theory of Riemann surfaces. They took the surface group as a fundamental group of Riemann surface. They took finite sheeted cover and they play with the finite sheeted cover to show that you can solve this equation. So it's another completely different technique which they brought in to the study of stability. I think this is the charming of this subject, that we have a problem here which can be attacked from several very different techniques. Each of them is suitable for some different groups.
Now, there's a question by Desi Kushlakova.
Hi, Alex. I have the following question. What about the Thompson group F, two generator, two relator group?
You mean the simple groups?
No, the F, which has, it's two generator, two relator, and the commutator is simple.
Right. They're almost simple, yeah. We don't know. You see, it will be great.
We don't know whether it's amenable, actually. I think it's an open problem whether it's amenable.
Oh, it's not even known if it's amenable. Yeah, right. So if you would prove that it's stable, then you solve two major problems at the same time. You prove that it is non-amenable, because an amenable stable group must be reduced fine, but it is also non-sophic. And maybe actually, when you say that, might be a good idea to study the IRSs of it, because assume if you get some knowledge of the invariant random subgroups of it, and now there might be a chance to get some understanding. Maybe, I don't know. Then. Okay. There is very little chance that the IRSs here will be dense, unless there is no real non-trivial IRS. Yeah, okay. I don't want to bother the audience. It's something worth thinking about, but I don't know. I really don't know. I never thought too much about that group. All the kind of simple groups are kind of good candidates for being non-sophic. So if you prove to one of them simple or close to be simple, that they are stable, you solve the Gromov problem. There are these finitely presented simple groups of also Burger and Moses. So that because the relations there are very, very simple to express. They are kind of very short. And if one could prove about them that they are stable, then they are non-sophic, which is, some people believe that they are indeed non-sophic, but nobody knows to prove it.
Okay, more questions?
Could you please show the last result on the bottom of your last slide, please? That was from the audience.
What, to show the last result?
Yes, thank you.
Okay. This theorem 12 of Johanna. Yeah, Johanna became a pretty active player in this. He is in San Diego, and this area is kind of combination of C-star algebras and geometric group theory. And he brought also some new methods to the game. So he proved that, just think about it, the following was an open problem. Just take two free groups and take the product of them. None a billion free groups. Because otherwise it would be Z cross Z. And none a billion free groups, just take the direct product of them, they are not stable. If you think about it, then it's a bit crazy, because you see, it says you have two generators, A, B, and X, Y. And A, B are free, and X, Y are free, and they just commute with each other. So, and I send A, B, X, Y to permutations, now the A and B, I don't have to correct each one by itself. The X and Y, I don't have to correct each one by itself. Now I have to correct that A and B, which are almost commute with X and Y, should be commute. I can correct A to commute with X because Z cross Z is stable. I can correct A to commute with Y. I can correct B to commute with X. I can correct B to commute with Y. But I cannot correct the four of them to all, so that the first two will commute with the other two. So this can be presented as a very, very, very simple statement that you can explain and at a second-year undergraduate, but the proof is fairly deep.
Okay. More questions? I have time to one question.
Well, I have two naive questions towards your present, actually. First, my question is whether stability is a profinite property.
We don't know. Now, when you ask that, I ask myself, oh my God, why didn't I think about that? It's so natural for me to think about it, especially I have some student working on stability. I have some student working on profinite rigidity property. Why didn't I tell them to talk to each other?
Well, my second question,
that's a good question, which at this point I don't know. I should think about it. That's very good question.
And second, can one extend stability to profinite groups, to consideration to profinite groups at all? Or, I mean,
sorry, say it again, please.
What about stability for profinite groups? Is it possible to state it reasonably and?
Okay. Again, I cannot answer intelligent question right away. I should think about that. What you have to do is to come up with a kind of an almost. What is an almost homomorphism? What does it mean? An almost action of a profinite group on a finite set. Yeah, I have to think about it. That's a good question to suggest another line of research if it can work.
So thanks. Again, the speaker, please.
Thank you very much. I'm really sorry I was
Thank
not
you for
able
your beautiful talking.
to be with you.